The Maxwell-Boltzmann distribution is a model that we use to think about molecules of gas inside a container. And we use it when we're thinking about the energies that the molecules of the gas have. So if we take a look at this distribution, on the x-axis we have number of molecules, and the y-axis has the speed, and sometimes that's labeled as kinetic energy because that's related to the speed of the molecules. And you can see it's a nice smooth curve. I want you to notice that it is asymmetrical. If we look at where the peak is, if I were to draw a line, a vertical line at the peak, there's a little bit more area on the right-hand side than the left-hand side. So here, when the speed goes down to zero, we have zero molecules that are traveling at a speed of zero. It's not really possible for molecules to have a speed of zero because that would only happen if their temperature is zero, theoretically. And we know we can't reach zero temperature. And if we look at the higher speeds, we see that this tails off more gradually. Okay, so it's a little bit asymmetrical. Now, it's the way that you would come up with a graph like this, if you were actually going to take some measurements. What you might do is take a look at the particles inside a container, count up how many particles, how many molecules have a speed of zero. That's always going to be zero. See how many particles are going a little bit faster. See how many particles are going a little bit faster than that. And so if you think of it more like a histogram or a bar graph, then what we have is sort of bins of molecules of different speeds. So this bin has the slowest molecules in it. There's 3 molecules that are going this speed. 6 molecules are going this speed here. This is the most common speed that a molecule is going. And then we have 1 molecule over here that's going way faster than the other molecules. So you can see that asymmetry, okay, that we've got a peak here, but things are decreasing really quickly as we go down to zero, and they're decreasing more slowly in the other direction. And we could count up all of the molecules here, 3 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, and that would tell us the total number of molecules that we're looking at. And the curve is just telling us what speeds are most common. Okay, so where the peak is, that's the most common speed we have. If we were looking for the average speed of all of these molecules, it would be a little bit higher than this. Okay, so if this is the most common speed, the average speed would probably be more somewhere around here. You could actually figure it out, but because we have more molecules going faster than we do have molecules going slower, the average speed is always going to be a little bit beyond where that peak is. Okay, so the average would be not at the peak, but a little bit higher than that because we've got more molecules going faster than slower. If you think about some molecules in a container and if you think about heating them or cooling them, but keeping the same number of molecules in there, this green curve, the middle curve, is a room temperature gas. Okay, so we have, again, no molecules with a speed of zero, and then as the temperature gets higher, we still have some molecules that are going quite quickly in the mix, but the average speed of the molecules might be somewhere around here. If we were to cool all of those molecules down, you can see that the shape changes. We end up with more molecules going more slowly, but we don't have nearly as many molecules that are going quickly. So the area under the curve, which represents the number of molecules, has stayed the same, but the shape of the curve is different. So when we cool it down, we still have that asymmetrical shape. It's tailing off a little more in this direction, and it's taller. When we heat the gas up, we still have an asymmetrical curve. It's slowly tailing off to the right, but we can see the curve sort of flattens out. Okay, so each of these curves has the same number of molecules being counted. It's just that this distribution of speeds is different for each one. So if we just take a look at this simulation for a minute, we've got a graph over here, which is number of particles versus the speed the particles are going at. And you can see right now it's an experimental value, but it is following that Maxwell distribution. We have some molecules going slowly. The most common speed is right around here, and then it's tailing off to the right. We have some molecules going quite quickly. If I heat this up, my container, we can see the shape of that curve change. So we end up with more and more molecules that are going more quickly, but the same number of molecules is in there as was in there before. Okay, so the Maxwell-Boltzmann distribution always tails off. Ooh, I blew the lid. Let's return the lid. I've never done that before. So the distribution can be a little more flat when things are warmer. And if you cool it down, you have way fewer molecules that are going super quickly, and you start to get a taller peak. But if you added up all the molecules in there, it's always the same number of molecules. It's just that their speeds are different. And you can see when you look at this simulation, some of those molecules are going more quickly, some are going more slowly, and the temperature just tells us something about the average speed of the molecules. Let's cool that down again, and you can see the shape of that curve change. So we're slowing the molecules down. Now we've got a higher peak over here. At the slower speeds, very few molecules are traveling quickly anymore.